In this video, we're going to talk about exact differential equations. Differential equation in the form of m of xy dx plus n of xy dy is equal to 0 is exact if the partial of m with respect to y is equal to the partial of n with respect to x. And we'll have a process to go through to solve that. If you have taken calculus 3 and you have found a potential function, f of xy, starting with a equation similar to this, then this is basically the same thing. So in some cases, we can make a differential equation exact using an integrating factor like what we did last time with linear differential equations. We just didn't know about exact differential equations, and that's what that integrating factor was doing. But that's actually what we did last time, using the integrating factor that mu is equal to the to e to the integral of p of x dx. So when it was written in the form of dy dx plus p of x y is equal to f of x, and we made it exact that way. So a couple of the common integrating factors that we're going to use are when we need a integrating factor mu that is a function of x, we'll use e to the integral of the partial of m with respect to y minus the partial of n with respect to x in the numerator, all over the original n. And then that's going to be integrated with respect to x. If we need a integrating factor mu that's a function of y, then we're going to use e to the integral of numerator n, partial derivative of n with respect to x minus partial derivative of m with respect to y, and we'll divide that by our original m, and then integrate with respect to y. When we do these integrations, then we may have to look at these things like we're doing the opposite of partial differentiation, where the other variable is held as a constant. So be careful when using this technique with making something exact that's not exact, when you have other things that may be available to you. Don't use this technique as a first choice, because it has the potential to add or possibly remove solutions. It's kind of like you don't multiply both sides of the equation by x or divide both sides of the equation by x in algebra, because you could potentially or a function of x, because you could potentially add or remove solutions that weren't there originally. So let's go ahead and let's look at some examples here. So first example we have is going to be 2x minus 1 dx plus 3y plus 7 dy is equal to 0. So I first want to check to see if the partial of this first part, m with respect to y, since there are no y's there, that's going to be 0. dn dx, since there's no x's here, that's going to be 0. So they are equal to each other, and I can use this method of exact differential equations. So what I'm going to do is choose one of these parts, it doesn't matter which one, and say that this is already the derivative of my function with respect to that variable. So I'm going to integrate with respect to whichever differential I see there. They're both pretty easy, so let me just pick the first one here and do a integration here. So this is going to turn into x squared minus x plus some g of y. It's not just going to be a constant this time, because if I have something that had just y's in it, when I take the partial derivative with respect to x, then all of those y's are going to also go to 0. Hopefully you have learned about partial derivatives already. So now I'm going to say that df dy, the partial derivative with respect to y here, is going to be g prime of y, and that needs to be equal to n of xy, which is 3y plus 7. You don't always get all these terms that drop out, but in this case we did. I'm going to integrate both sides here and say g of y is equal to 3y plus 7 dy, which is going to be 3/2 y squared plus 7y. And now I can just put generic plus c because my constant is incorporated into that g of y. So my f of xy here is going to be x squared minus x plus 3/2 y squared plus 7y plus c. If I would take the derivative of this original function partially with respect to x, I'd get 2x minus 1. If I take the derivative of this partially with respect to y, I get 3y plus 7. This is an exact differential equation here. All right, let's go ahead and delete all that. And come on back up here. Let's skip down here to number 7. X squared minus y squared dx plus x squared minus 2xy dy equals 0. So let's take the derivative of this piece with respect to y. Partially is going to give me a negative 2y. And this one with respect to x is going to give me two x minus 2y. So so not exact, right? And if you wanted to go through the process of trying to use one of these integrating factors to make it exact and see what would happen, you could do that. But this example just asks to say if it's exact, and if so, find the answer. If it's not exact, just say that it's not exact. So there was an example of one that was not exact. Moving on here to this one is ln of y minus e to the negative xy dx plus 1 over y plus x ln of y dy equals 0. So let's take the derivative of the first part with respect to y. So that's going to be a product rule here. So that's going to be derivative of m with respect to y is going to be ln of y plus 1 minus, and then a negative x times that makes a positive x e to the negative x y. So I took the derivative of this exponent with respect to y, got a negative x, multiplied that by the coefficient up front to get a positive x, left the e to the power alone. So now I want to see partial of n with respect to x. And so that first part goes away and becomes 0 plus ln y is just simply ln y. So this one is not exact. Either. So you can have some fun again trying to make that exact if you would like to, but don't worry about that until the instructions in the assignment tell you to try to make something exact using an integrating factor. Let's go ahead and solve an initial value problem that is possibly an exact differential equation. I haven't done one of these initial value problems in a while, but to show you that there's different types of initial value problems. 2xy plus x squared minus 1 dy equals 0. And I'm going to tell you that y of 1 equals 1. So that implies the 0.11 is that needs to be an answer to this when we're done. So, and it's going to be equal to the f of xy. We like to set it equal to 0 when we solve here. So, but we could just as easily set it equal to c, and that'll work, and we can solve for the c. All right, let's go ahead and find the derivative of this piece with respect to y. So before we do that, let's just make this x squared plus 2xy plus y squared dx plus, this is already expanded. So partial of m with respect to y is going to be 2x plus 2y. Partial of n with respect to x will be 2y plus 2x. So they do equal one another. I'm going to integrate over here with respect to y. So f of xy is going to be 2xy squared over 2. That's going to be an x y squared plus x squared y minus y plus a g of x. So df dx, which is going to be my m, is going to be y squared plus 2xy plus g prime of x. And I'm going to set that equal to x squared plus 2xy plus y squared. So the y squared term will zero out, and the 2xy will zero out. My g prime of x therefore needs to be equal to x squared. So g of x is equal to 1/3 x cubed plus c. That means that my f of xy is equal to xy squared plus x squared y minus y plus 1/3 x cubed plus c. And I'm just going to say that this is going to be equal to c here, is what I'm going to do. Instead of plus c equals 0 and bringing the generic constant over, I'm just going to say that it's going to be minus c equals 0 and bring the generic constant over. So this is going to be f of 1, 1 is going to be 1 times 1 plus 1 times 1 minus 1 plus 1/3 times 1 cubed is equal to C. So 1 plus 1 is 2 minus 1 plus 1/3. 1 plus 1/3 is 4/3. So 4/3 is C. So we come back here. We say that that means that f of xy is equal to xy squared plus x squared y minus x plus 1/3 x cubed is equal to 4/3. All right, that'll be it for this video. I didn't do any examples of making something exact, but you can find those examples in your book if you would like. And they would be like number 29 and 30, or 31 through 36, or 37 through 39. Those all find appropriate integrating factors. You also find a proof in your book of how what we did with linear differential equations was making this an exact differential equation, and how we could use this idea of exactness then to say that we had exactly the product rule on the left-hand side of the equation, and we could write that derivative of that product rule is equal to the right-hand side when we had multiplied by the integrating factor, and then we could integrate both sides to get rid of the derivative. And that's how we were solving our linear differential equations last time, was by making them exact like this, by using a rule that we knew was the exact derivative of something, namely the product rule. All right, so that's it. We'll come back next time and we'll talk about solutions using by substitutions. One of the important things when you see something really messy over and over again in the problem, you might want to use a U substitution and try and change what you have into something that is separable, linear, or exact. All right, see you for the next video.